Welcome to my talk, Asymptotic Theory and Bootstrap Inference for Mack's Model. My name is Steinmetz, and this is joint work with Carsten Jentsch. So here you see a typical process of a loss adjustment for a non-life insurance contract. Typically, the contracts last 1 year, and during the contract period, a claim may happen. With some delay, the claim is reported to the insurance company. As with some further delay, the insurance company makes some claim payment. Hence, it takes several years until a claim is fully paid. But by law, insurance companies need to set capital reserves to pay for all outstanding claims. So hence, an accurate prediction of all outstanding claims, whether the claims are known or still unknown, but all happened so far, is necessary to ensure the solvency of the insurance company. So therefore, the claim data is organized typically in a so-called loss triangle, where the claims are sorted by their accident year, which is basically the contract year and the year of development. By using this organization scheme, we get the triangle structure of the data. And here we look at the cumulative claims, and hence the observed upper triangle represents the observed claims at time I, and note this diagonal represents the last observed claims at time I. Based on this table, we want to derive all outstanding claims, which is basically the last column of this table. And then using all outstanding claims, which need to be estimated minus the diagonal element, we get the reserve. And then we are just summing up over the individual reserves to get the total reserve. So how can we estimate the reserve? Therefore, one famous model is the so-called Mack's model. It's a distribution-free model, and it's a deterministic one. It has three basic assumptions, where the first one and the second one refers to the conditioned moments of the claims. And so the first one, we take into account some development factors to calculate the conditioned expectation of the claim. And also we have some existing variance parameters. They need to are taken into account to calculate the conditioned variance. And the cumulative payments are stochastically independent over the accident years. So since the development factors and the variance parameters, they are unknown, they need to be estimated. And here you can see it's estimators. And then using the estimator of the development factor, we are able to calculate the best estimate reserve. And then we also can sum up over the individual reserve to get the total reserve. And also Mack gives us a formula to calculate the mean squared error of the reserve, but still knowing only the first two moments of the reserve, this is not sufficient, especially if we are interested in higher quantiles of the reserve. So therefore we define in the following a general stochastic framework to apply later on some asymptotic theory for the reserve. So our first assumption relies on the first column entries. These are ID random variables with some existing second moment. And the claims can be constructed by a recursive model, where we define also some new random variables called individual development factors conditioned on the previous claim, and they're positive and they're independent over the rows. Further, these individual development factors fulfill certain distributional assumptions which come directly from Mack's model. In addition, we need some parameter assumptions, so the development factors decrease fast to 1 and the variance parameters decrease fast to 0, such that these two statements hold. then using these assumptions, we are able to define a central limit theorem for the development factors. So, and then further, we look at the predictive root of the reserve, which is the stochastic prediction model minus its best estimate. And if we look closer on it, we can split it into two additive parts, where the first part captures the process uncertainty and the second one captures the estimation uncertainty. So for the first one, conditioned on the diagonal, we can say that this one converges in distribution to a non-degenerated distribution, which has mean zero, and the variance looks like this. And for this first part of the predictive root, we can say that this limiting distribution will be typically a non-Gaussian. It is neither possible to show asymptotic normality or to disprove it, since Lindenberg's condition and the Feller condition both do not hold. But nevertheless, the distribution could be Gaussian if conditional on the diagonal or summands are jointly Gaussian. In contrast to the first part, the second part is measurable with respect to the complete upper triangle. So therefore, the limiting distribution looks a little bit different. So we need to inflate it with the square root of I and get the following limit distribution T2, where T2 is generated by the Euclidean product of the stochastically independent sequence of x and y, and x and y denotes a centered Gaussian process with the following covariance, and x is a sequence that has the distribution coming from the first row. So looking now, we want to derive the limiting distribution of the predictive root, and since we have derived the limiting distribution separately from the first and the second part, and we can say, since the first part it dominates asymptotically, we can say then, conditioned on the diagonal, the limiting distribution of the predictive root converges to the distribution of the first part of the predictive root, where so hence asymptotic normala in general for the reserve does not hold, and normal approximation will be in generally not valid for statistical inference. Especially we have seen in our short simulation study that the resulting limiting distribution will generally depend on the specific family of the distribution of the individual development factors. So since it's hard to derive the distribution of the predictive root directly, a bootstrap approach would be nice to estimate the predictive root. So therefore, given the upper triangle, we estimate the parameters, and then we can resample the bootstrap first column entries by resampling from the observed first column entries, and then we are generating a bootstrap upper triangle by simulating recursively the individual development factors, such that the following assumptions hold, and by choosing accurate distribution for the individual development factors. And then, having this in mind, we are able also to construct a bootstrap predictive root of the reserve. And again, this predictive root can be again split into two additive parts. And for both parts, independently, we can show the consistency. So under some mild regularity conditional on the diagonal, the difference between the first part of the predictive root and its bootstrap version vanishes, where we look here at the Mellus metric. And analogously, we can also show the consistency of the second part of the predictive root, where it needs to be inflated with the square root of I, and also here still the difference between the distribution is vanishing, where we also consider here the Mellus metric. So as a conclusion, I want to sum up. We derived some asymptotic theory, and this is necessary to get a deeper understanding of the predictive root of the reserve. And in particular, it allows us to construct a suitable bootstrap methods and to prove their consistency. So in future, we want to look at Mack's residual-based bootstrap and want to check whether this one is actually consistent, and especially in which sense. In addition, we want to check under which conditions the limiting distribution of the first part of the predictive root conditioned on a diagonal will be a Gaussian distribution. Thank you very much for your attention.